So let's consider sets of numbers. A common description that we're all kind of familiar with is an even number. Right? We can say n is an even number. What does that mean? We can say n is an element of E. Right? Notice element here, call capital E here, is another way of saying this. As an even number, n is an element of this E, where E is the set of even numbers. Well, that's not really so helpful so far. Where this is helpful is that it enables us to have a more clear definition of what these things are when we say it's an even number. So now we can define E we can say x divided by 2 has no remainder. And that's what we mean when we say it's even. We mean it's divisible by 2. Right? Or we could say x is divisible by 2. Or we could start to get fancy and say x is a multiple of 2, which is another way of saying x equals 2 times a, where a is an element of capital N. Now, this is a new symbol that we're about to define. When we say it's a multiple of something, we're talking about 2 multiplied by some number, but not just any number. Right? I could have 2 times pi, or 2 times 3/7, or 2 times the square root of 11. Right? Those are all 2 times something. I could divide anything by 2. I can take 33, divide that by 2. Right? When we say it's divisible, we're saying this division leaves me with a whole number and nothing else. Right? I could say 33 halves plus 0, no remainder here. When we're talking about the realm of remainder, divided by 2. I'm assuming that this answer is a whole number, that I'm starting with a whole number, dividing by 2 to get a whole number. I'm not starting with some weird expression. Right? By weird meaning non-whole number pieces. But we deal with non-whole numbers all the time in this class and in all the classes moving forward. So we have to be clear, are we talking about whole numbers, or are we talking about all real numbers or all rational numbers? I could toss a negative in here. 2 times negative square root of 11. Right? We have to know what kind of numbers we're talking about. And that's why we have all this set theory background, is so that we can define these sets and their relationship to each other. So capital N with this extra line is a symbol we use for the natural numbers. Right? That's things like the counting numbers. Now, our textbook is on one side of a debate that about half of all textbooks are on, and the other half of textbooks on the other side of the debate on whether or not 0 counts as a counting number. According to our textbook, the natural numbers only consists of 1 and so on. This set, we don't get a special symbol for it because it's basically the same thing. We call, let me just bend that around here, whole numbers. Right? So we'd say the natural numbers are a subset of the whole numbers. Because if I'm listing them out here, I'm listing all of these, and I'm also listing something else. Right, so this is a larger set. It has every element in this set plus another one. The next largest set includes definitely 0 and all the other counting numbers, but it also includes their opposites. We call that the integers. And it's very common for people to misspell this. It's not integer, it's integer. So the integers are counting numbers, whole numbers, natural numbers, whichever word you want to use for it. Counting numbers, it's an S. And their opposites. And for that, we use kind of a sideways N, which you might recognize. Make these a little straighter. It's capital Z. It's for the German word for number, starts with a Z. So N for natural numbers, Z for integers. So using our new notation here, we would say N is contained within Z. If I drew these as circles, I'd have all of my N's here, and then in addition to that, we add 0. There's my whole numbers. In addition to that, so there's just one number here. Then I have all these other numbers, -3, -5, -9,000, as opposed to +3, +5, +10 billion, and 6. Right, all of these whole numbers are contained within this larger set of integers. And these numbers exist because of what we know about adding and subtracting. Right? You can add two whole numbers, you get more whole numbers. Right? You can add this amount to some other amount, or rather add this amount to some previous amount, we just get a bigger whole number. But if we start subtracting, sure, you can subtract 3 from 10, but if you try to subtract 13 from 10, you need a number to represent that. That's why we have integers, right? So now we can always add or subtract, and there's a number to represent the result of that. Results of differences are sometimes negative. Results of sums of positive numbers are always going to be positive. Now that we can input negative numbers, the output might be positive, it might be negative, we don't know. But if we put in any of these numbers to a sum or a difference, we're going to get back another one of these kinds of numbers. But we don't just add and subtract, we also multiply, and the inverse of multiplying is dividing. So I can multiply two whole numbers. 2 times 4, 8, another whole number, great. 3 times 10 billion, 30 billion, another natural number, great. Multiply these, -8 times 3, Negative 24, fine. Negative 8 times negative 2, positive 16, fine. That's all going to be on my list. But as soon as I take the inverse of multiplication, as soon as I start dividing, I'm into trouble, right? So 8 divided by 4, 2, no problem. 8 divided by 3 doesn't go in evenly, right? I need a new number to represent that. If I put 8 on the number line and I cut it into 3 pieces, I need a name for that spot on the number line, right? So that name is 8/3. That's what we call a rational number. And here's our formal definition of a rational number. Some mistake there. Oh, we didn't want to resolve that. Okay, let me just erase a little bit. There we go. Where A and B are elements of, started to write an N, but I meant to write Z. So what does it say? This set Q represents all X that are equal to this what? What do we call this thing? Call it 3 different things, right? Sometimes we call it a fraction. When that works out nicely to a number, to a whole number, we're more likely to use this other word for it, which is a quotient. Get the output for that division. So 8 divided by 3, the quotient is 8/3. But we also talk about 8 to 3 as a ratio. And it's this word quotient that gives us the Q symbol, and it's this word ratio that gives us the name. This is the set of rational numbers. So 8/3 is a rational number, 2 is a rational number. Anything that we could write it as a ratio of integers. So something like -7 to 6, integer, that's a rational number. -15 to -25, integer, rational number. Now, when we describe rational numbers, it's nice to have one number per spot on the number line. So we usually talk about them in their reduced form, right? So that's 5 times 3, that's 5 times 5, both negatives, that cancels. Right, so the name for this rational number, we call it 3/5. But we don't need to know its name if we're just deciding is it in or is it out. This is in because we have a rational to an integer in relation to another integer, the ratio of those two. So there's our rational numbers. And that's most of what we're dealing with up to this point. Now we can add, subtract, multiply, and divide. There's just one problem. What about roots?